Hello and welcome to Sleepy Physicist. I'm so glad you're here. Whether you're settling into bed with your thoughts wandering toward the infinite, curling up on the couch after a long day of earthbound concerns, or simply trying to let your mind drift into something larger than the everyday, you found the right place. This is our quiet corner of the internet, where the cosmos gets contemplative, where physics puts on its pajamas, and where the incomprehensibly vast becomes a gentle companion for your evening reflections. Tonight, we're embarking on a journey that will challenge the very limits of human understanding. We're going to explore something so mind-bendingly enormous that our brains, quite literally, cannot fully grasp it. And yet, in trying to comprehend the incomprehensible, we might just discover something profound about the nature of existence itself. Before we begin, if you find these slow explorations through the mysteries of physics helpful for unwinding your thoughts, I'd be ever so grateful if you tapped the like button, subscribed, or simply left a comment telling me where in the world you're listening from tonight. Are you watching from a bustling city where light pollution hides the stars, or perhaps from somewhere remote where the Milky Way stretches across your sky like a river of ancient light? I love hearing from fellow travellers on this cosmic journey. Now, I do hope this video isn't so fascinating that it keeps you awake, but if it does, at least you'll drift off with your mind expanded by the sheer wonder of what lies beyond our little blue dot. A fair trade, I'd say. Here's something that will make you pause and question everything you think you know about scale. If you held a grain of sand at arm's length against the night sky, that tiny speck would cover a patch of space containing thousands of galaxies, each harbouring billions of stars. Every seemingly empty point of darkness above you is actually teeming with more worlds than existed in the imagination of every human who ever lived. This isn't poetry, this is physics, and it's just the beginning of our journey into the mind-bending reality of cosmic scale. Take a deep breath, let yourself settle. Tonight we're going to gently explore why the universe might be fundamentally incomprehensible to creatures like us, and why that incomprehensibility is actually one of the most beautiful aspects of our cosmic story. Let's start with something wonderfully deceptive about human perception. Right now, as you sit wherever you are, everything around you feels manageable, understandable, human-scaled. The room you're in has walls you can see, dimensions you can pace out. If you walked outside, you'd find a neighbourhood with streets that make sense, a horizon that feels comfortably distant. Your entire lived experience has trained your brain to navigate a world measured in meters and kilometers, minutes and hours. This is the cosmic joke we're all living inside. Our brains evolved over millions of years to help our ancestors navigate environments where the biggest concern might be spotting a predator across a savanna or judging the distance to the next watering hole. We developed an intuitive understanding of scale that served us beautifully for survival, but leaves us utterly unprepared for the reality of the universe we actually inhabit. Consider this. The distance from your eyes to this screen right now is probably less than a meter. That distance feels immediate, manageable. You could reach out and touch it. Now try to imagine a light year, not just the number, but the actual distance. A light year is how far light travels in a year, moving at roughly 300,000 kilometers per second. That works out to about 9.46 trillion kilometers. Already your brain is starting to give up, isn't it? That's not a failure of imagination, it's a feature of human cognition. We simply don't have the neurological architecture to truly comprehend such scales. It's like asking a calculator to compose a symphony or a fish to appreciate a sunset. The tools aren't there. But here's where it gets even more wonderfully absurd. That incomprehensibly vast distance of 1 light year, it's essentially nothing on a cosmic scale. The nearest star to our Sun, Proxima Centauri, is 4.3 light years away. Our galaxy, the Milky Way, is about 100,000 light years across. And the observable universe, it stretches roughly 93 billion light years in diameter. Let me put that in perspective with an analogy that might help, though even this analogy involves scales that stretch our understanding. If the observable universe was scaled down to the size of a football field, our entire Milky Way galaxy would be the size of a grain of rice. Our solar system, that vast realm containing 8 planets, countless asteroids, and the space between Earth and Pluto that we consider so impressively large, would be too small to see with the naked eye. And yet that grain of rice contains somewhere between 100 and 400 billion stars, each potentially hosting its own family of worlds. The scale is so ludicrous, so beyond human comprehension, that we can only approach it through metaphor and mathematics, never through true understanding. Now, you might wonder how we even know these cosmic distances. After all, it's not as though we can stretch a measuring tape across the galaxy. The story of how humans figured out the scale of the universe is itself a testament to our species' remarkable ability to transcend the limitations of our evolved perspective, even if we can't quite comprehend what we discover. It begins with something called parallax, a technique so elegant it feels almost like cheating. Imagine holding your finger at arm's length and closing one eye, then the other. Your finger appears to jump back and forth against the background. This apparent shift is parallax, and it's the foundation of our cosmic measuring system. Astronomers use the same principle, but instead of closing one eye and then the other, they observe a nearby star from one side of Earth's orbit, then wait 6 months and observe it again from the opposite side. The star appears to shift slightly against the backdrop of more distant stars. Using trigonometry, they can calculate the distance to that star. But here's where the elegant simplicity meets cosmic absurdity. The largest parallax angle ever measured belongs to Proxima Centauri, our nearest stellar neighbour, and it's less than 1 arc-second. To put that in perspective, 1 arc-second is like trying to spot a coin from 2 miles away, and that's for the closest star. Most stars show parallax angles thousands of times smaller. The precision required is staggering. We're measuring angular shifts smaller than the width of a human hair, viewed from several kilometers away. It's a testament to human ingenuity that we can measure such tiny angles at all, and yet this represents just the first rung of what astronomers call the cosmic distance ladder. Beyond parallax, we need different tools. There are special types of stars called Cepheid variables that pulse with a brightness directly related to their intrinsic luminosity. By measuring how quickly they brighten and dim, astronomers can calculate how bright they actually are, then compare that to how bright they appear from Earth to determine distance. These cosmic lighthouses can be spotted in nearby galaxies, extending our reach to millions of light years. For even greater distances, we need even brighter standard candles. Type Ia supernovae, the explosive deaths of certain white dwarf stars, all reach roughly the same peak brightness. When we spot one of these cosmic explosions in a distant galaxy, we can use it as a measuring post for distances of billions of light years. Each step in this cosmic distance ladder extends our vision deeper into space, but also accumulates uncertainties. By the time we're measuring the most distant objects we can observe, our measurements carry the accumulated errors of every previous step. We're like explorers mapping an unknown continent by taking careful steps, but each footstep introduces a small error that compounds over the vast journey. And yet, through this painstaking process of measurement and remeasurement, calibration and recalibration, we've mapped the universe out to its very edge. The edge of the observable universe, that is. What lies beyond remains one of the most profound mysteries in all of science. This brings us to one of the most mind-bending concepts in all of cosmology: the difference between the universe and the observable universe. When we talk about the universe being 93 billion light-years across, we're actually talking about something quite specific and limited. We're talking about the observable universe, the sphere of space from which light has had time to reach us since the Big Bang. But here's where things get deliciously strange. The universe is 13.8 billion years old, so you might expect that we can see objects that are 13.8 billion light-years away. But that's not quite right. The most distant objects we can observe are actually about 46.5 billion light-years away in any direction. How is this possible? The answer lies in the expansion of space itself. While those ancient photons were travelling toward us for 13.8 billion years, the space through which they travelled was expanding. The galaxy that emitted the light we're receiving today has been carried away from us by cosmic expansion, and it's now much farther away than it was when it first sent out that light. It's a bit like trying to reach someone on an escalator that's moving away from you. Even if you walk toward them at a steady pace, the distance between you might still increase if the escalator is moving fast enough. In the case of the universe, space itself is the escalator, and it's been moving this whole time. This creates what cosmologists call the cosmological horizon. Beyond this horizon, roughly 46.5 billion light-years away, there are regions of space from which light has not yet had time to reach us. Those regions might contain galaxies, stars, planets, perhaps even other forms of life, but we will never see them unless we wait longer. And even then, the expansion of space means that some regions are moving away from us faster than light can travel through the expanding space between us. This isn't a violation of Einstein's speed limit. Nothing is actually moving through space faster than light. But space itself can expand at any rate, carrying distant objects away from us at effective speeds that exceed the speed of light. It's one of those cosmic facts that sounds impossible, but follows naturally from the mathematics of general relativity. What this means is profound. There are entire regions of the universe that are forever beyond our reach. No matter how long we wait, no matter how powerful our telescopes become, no matter how advanced our civilization grows, there are parts of reality we will never observe. The universe has built-in horizons beyond which even light cannot travel to bring us information. And if that weren't humbling enough, consider this. Most cosmologists believe that what we call the observable universe is just a tiny fraction of the total universe. Recent estimates suggest that the whole universe might be at least 250 times larger than what we can observe. If that's true, then our observable universe, containing its 2 trillion galaxies and 10 to 24 stars, represents less than 1% of cosmic reality. Some theories suggest the universe might be infinite in extent. Infinite. Let that word settle in your mind for a moment. If the universe is truly infinite, then everything that occurs within our observable bubble must occur again and again, an infinite number of times, in regions beyond our cosmic horizon. Every possible arrangement of matter and energy, every possible variation of cosmic evolution, every possible story, including yours, playing out endlessly across an infinite expanse. The mathematics of infinity suggests that somewhere out there, in regions we'll never see, there are perfect copies of you, living lives identical to yours in every detail, and also versions living lives that differ by just one decision, one quantum fluctuation, one butterfly wing beat that changed everything. An infinite universe doesn't just mean more of the same, it means everything possible, repeated without end. As we've journeyed outward from our local cosmic neighbourhood, we've discovered that the universe isn't just big, it's organised on scales that stretch the imagination. Galaxies aren't scattered randomly through space like stars scattered across a night sky. Instead, they're arranged in an intricate pattern that astronomers call the cosmic web, picture soap bubbles floating in a bathtub. The bubbles themselves are mostly empty space, but where their surfaces meet, you get dense lines and intersections. The universe is structured remarkably similarly. Vast empty regions called cosmic voids, containing very few galaxies, are surrounded by thin sheets and filaments of galaxies. Where these cosmic filaments intersect, you find the densest galaxy clusters. These structures operate on scales that make our previous discussions of galactic distances seem almost quaint. Individual galaxy filaments commonly stretch 160 to 260 million light-years across. The largest known structure, possibly the Hercules Corona Borealis Great Wall, spans roughly 10 billion light-years. That's more than 1/10 the diameter of the entire observable universe. To put this in perspective, if our Milky Way galaxy were the size of a coin, this Great Wall of galaxies would stretch from Earth to the Moon and back again several times over. And this is just one structure among millions that make up the cosmic web. Our own galactic address reveals just how nested these cosmic structures are. We live in the Milky Way galaxy, which is part of the local group of galaxies, which is part of the Virgo supercluster, which is part of the larger Laniakea supercluster, which is part of the Pisces Cetus supercluster complex. Each level of this cosmic hierarchy is vastly larger than the last. The local group, containing our Milky Way along with Andromeda and about 52 other smaller galaxies, spans roughly 10 million light-years. The Virgo supercluster, containing thousands of galaxy groups like ours, spans about 110 million light-years. Laniakea, containing the Virgo supercluster, and many others, spans 520 million light-years and contains the mass of about 100 million billion suns. And Laniakea itself is just one of an estimated 10 million superclusters in the observable universe. When we zoom out to see the full cosmic web, something remarkable becomes apparent. The universe looks remarkably similar at different scales. The same filamentary, bubble-like structure that we see in the cosmic web appears in computer simulations of how dark matter behaves on the largest scales. This suggests that the architecture of the universe is shaped by fundamental forces operating across scales that span from the quantum to the cosmic. But here's what makes this even more mind-bending. All of the matter we can see, all of the stars and galaxies and gas clouds that make up this magnificent cosmic web represents less than 5% of the total contents of the universe. The other 95% consists of dark matter and dark energy, mysterious components that we can't directly observe, but which dominate the structure and evolution of everything we see. Dark matter provides the gravitational scaffolding on which the cosmic web is built. Dark energy drives the accelerating expansion of space itself, determining the ultimate fate of all these grand structures. We live in a universe where the vast majority of reality consists of phenomena we can't see, touch, or directly detect. Our entire visible cosmos is just the foam on an ocean of invisible substance. As we continue this journey into the incomprehensible, we'll explore what these discoveries mean for creatures like us, evolved to navigate a world of familiar scales, trying to make sense of a reality that extends far beyond the boundaries of human intuition. As we drift deeper into this meditation on cosmic scale, let's pause for a moment and consider something rather extraordinary about the nature of measurement itself. Every distance we've discussed tonight, every mind-bending scale from the width of atoms to the span of superclusters, emerges from a universe that is fundamentally uncertain at its most basic level. At the quantum scale, the very foundation of reality operates according to principles that seem to mock our intuitive understanding of measurement and existence. Particles exist in multiple states simultaneously until observed. The act of measurement itself changes what is being measured. Position and momentum cannot both be known with perfect precision. The universe, it seems, is built on a foundation of beautiful, irreducible uncertainty. This quantum fuzziness doesn't just apply to tiny particles, it permeates every level of cosmic architecture we've explored. The atoms in your body, the elements forged in stellar cores, the gravitational waves that ripple through space-time itself, all emerge from this quantum substrate where certainty gives way to probability, where the very concept of definite scale becomes wonderfully elusive. Consider the profound implications of this. When we measure cosmic distances using our elegant parallax techniques and standard candles, we're ultimately relying on the behavior of photons, those quantum particles of light that somehow manage to carry information across billions of light years while maintaining their quantum nature. Each measurement carries within it the fundamental uncertainty that governs all quantum interactions. The cosmic microwave background radiation that fills the universe, that ancient afterglow of the Big Bang that we detect with our most sensitive instruments, is itself a quantum phenomenon. The tiny fluctuations in this background radiation, fluctuations so small they require extraordinary precision to measure, are what gave rise to the large-scale structure of the universe. Quantum uncertainty, amplified by cosmic inflation, became the seeds from which galaxies, stars, and ultimately consciousness itself would emerge. This creates a delicious paradox. Our brains, evolved to navigate a world of apparent certainty and solid objects, are actually quantum mechanical systems attempting to comprehend a universe built from quantum mechanical processes. We are uncertainty studying uncertainty, probability contemplating probability, quantum phenomena trying to understand their own quantum nature. Now, let's venture into the realm where numbers themselves begin to lose their intuitive meaning. We've been discussing cosmic distances in terms of light years and millions and billions, but these familiar words disguise something profound about the nature of large numbers and human cognition. When we say the observable universe contains approximately 10 to 24 stars, we're using a mathematical notation that hides the true magnitude of what we're describing. To write this number out in full, you would need to write a 1 followed by 24 zeros. That's a trillion stars. More stars than all the grains of sand on every beach and desert on Earth. But here's what makes this even more remarkable. Our brains can process the difference between 1 and 2, between 2 and 3, even between 10 and 20 with reasonable accuracy. But the difference between a trillion and a trillion? Cognitively, these numbers exist in the same category of incomprehensibly large. We've reached the boundaries of numerical intuition. This limitation isn't a failing of human intelligence. It's a feature of how consciousness itself operates. Our minds evolved to distinguish between quantities that mattered for survival, one predator versus two predators, 3 fruits versus 5 fruits. Natural selection never pressured us to develop intuitive understanding of quantities measured in powers of 10 with double-digit exponents. And yet, through the beautiful abstraction of mathematics, we can work with these incomprehensible numbers. We can add them, multiply them, use them in equations that describe the behavior of reality across scales that span from quantum fluctuations to cosmic evolution. Mathematics becomes our translator, allowing finite minds to engage with infinite concepts. Consider the mathematical relationship between scale and complexity in the universe. As we move from atoms to molecules, to cells, to organisms, to ecosystems, to planets, to solar systems, to galaxies, each level of organization exhibits emergent properties that couldn't be predicted from the level below. The mathematics that describes atomic behavior is elegant but tells us nothing about the nature of consciousness. The equations that govern galactic rotation reveal nothing about the experience of wonder you might feel while contemplating the night sky. This suggests something profound about the relationship between scale and understanding. Perhaps the universe isn't just incomprehensibly large in terms of distance and time. Perhaps it's incomprehensibly complex in terms of the layers of organization and meaning that emerge at different scales of observation. As we continue our gentle exploration of incomprehensible scale, we encounter one of the most beautiful and melancholy aspects of cosmic reality. The universe is so vast that most of it exists in a state of permanent isolation from the rest. Light, that fundamental messenger of information, travels at a finite speed. This creates what physicists call light cones, regions of space-time that can influence or be influenced by any given event. For us here on Earth, our light cone extends outward at the speed of light, roughly 300,000 kilometers per second, defining the boundary between the knowable and unknowable universe. What this means is profoundly moving. When you look up at the Andromeda galaxy on a clear night, you're seeing it as it was 2.5 million years ago. The light reaching your eyes tonight began its journey before the first humans walked upright. You're not seeing Andromeda as it is, but as it was when our species was just beginning to evolve the capacity to contemplate the cosmos. For more distant objects, this temporal displacement becomes even more dramatic. The most distant galaxies we can observe appear to us as they were when the universe was less than 1 billion years old. We see them as infant galaxies, just beginning to form their first generations of stars. Those galaxies, if they still exist, have had nearly 13 billion years to evolve, to form new stars, perhaps to develop planetary systems, maybe even to nurture life and consciousness. But we will never know what became of them. The light showing us their current state won't reach us for billions of years. And due to the accelerating expansion of space, we may never receive that information at all. There are galaxies whose light is reaching us right now that we will never see grow older. We see their youth, but their maturity is forever hidden beyond our cosmic horizon. This creates a universe filled with cosmic conversations that will never be completed. Every photon that reaches us from deep space carries news from the ancient past, but tells us nothing about the present state of its source. We live in a cosmos where the very act of observation is an act of archaeology, where looking outward in space is identical to looking backward in time. The implications are both beautiful and heartbreaking. Somewhere in the observable universe, perhaps many somewheres, there might be other conscious beings looking out at their night sky, seeing our Milky Way as it was billions of years ago, wondering if anyone might be looking back. They see our galactic past, we see theirs, but our present moments, the actual now of our existence, remain forever isolated from each other by the finite speed of light and the expansion of space. This cosmic loneliness isn't just poetic metaphor, it's built into the fundamental structure of space-time itself. The universe has evolved in such a way that consciousness, wherever it arises, finds itself isolated on islands of causality in an ocean of space and time, too vast for complete communication. As we've journeyed outward from our terrestrial perspective, we've encountered a universe organized into nested hierarchies of structure, each level vastly larger and more complex than the last. But this raises a fascinating question. Does this hierarchy continue indefinitely, or are there natural limits to cosmic organization? The structures we've explored, from galaxy clusters to superclusters to the cosmic web itself, represent the largest gravitationally bound or organized systems in the universe. Beyond the scale of superclusters, the expansion of space begins to dominate over gravitational attraction. This creates what cosmologists call the scale of homogeneity, roughly 300 million light-years, above which the universe looks statistically uniform in all directions. This scale of homogeneity represents something profound about the architecture of reality. It suggests that there are natural limits to complexity and organization, boundaries beyond which the fundamental forces that create structure give way to the fundamental expansion that drives structure apart. But even this apparent limit raises deeper questions about the nature of cosmic organization. Recent observations have revealed structures that seem to challenge our understanding of these limits. The Hercules Corona Borealis Great Wall, if it truly exists as a single coherent structure, would span nearly 10 billion light-years, far beyond what current cosmological models predict should be possible. These observations hint at something remarkable. Our understanding of cosmic architecture might still be incomplete. We might be like early cartographers who believed they had mapped the entire world, only to discover new continents beyond their known horizons. The possibility that cosmic structure extends beyond our current understanding creates a delicious paradox. The more we learn about the universe, the more we discover how much we don't know. Each answer reveals new questions, each measurement opens new mysteries. The incomprehensibility of cosmic scale isn't just a function of size, it's a function of the infinite depth of questions that each scale of observation reveals. Consider what this means for consciousness like ours, evolved to navigate environments measured in human steps and human lifetimes. We find ourselves not just small in a large universe, but simple in a complex universe, temporary in an ancient universe, local in a connected universe, finite in what might be an infinite cosmos. And yet, here's what fills me with quiet wonder. Despite these overwhelming scales and hierarchies, despite our infinitesimal size relative to cosmic structures, we conscious beings represent something unprecedented in the universe as far as we know. We are the parts of the cosmos that have evolved the ability to contemplate the whole. Every thought you're having right now about cosmic scale, every moment of wonder or confusion or awe represents the universe becoming conscious of itself through you. The atoms in your brain, forged in stellar cores billions of years ago, organized by evolution into patterns of extraordinary complexity, are now contemplating the very cosmic processes that brought them into being. In this sense, consciousness might represent the most remarkable emergent property in all the hierarchies of cosmic structure. Not because we're large, we're not. Not because we're long-lived, we're not. But because we're the universe's way of knowing itself. As we settle deeper into our exploration of incomprehensible scale, we must confront one of the most humbling discoveries in all of science. The vast majority of the universe consists of phenomena we cannot see, cannot touch, and barely understand. When astronomers first began mapping the rotation of galaxies, they discovered something impossible. Galaxies were spinning so fast that the gravity from their visible matter should have torn them apart long ago. Stars at the edges of galactic disks were moving as if there were far more mass present than anyone could detect. Either our understanding of gravity was wrong, or there was something massive and invisible providing the extra gravitational pull needed to hold galaxies together. This led to the discovery of dark matter, a form of matter that interacts gravitationally but doesn't emit, absorb, or reflect light. Dark matter makes up roughly 27% of the universe's total mass energy content. It provides the gravitational scaffolding on which all visible structure in the universe is built. But dark matter, mysterious as it is, isn't the strangest component of cosmic reality. That distinction belongs to dark energy, which makes up approximately 68% of the universe. Dark energy appears to be causing the expansion of space itself to accelerate, driving distant galaxies away from us at ever-increasing rates. Let this sink in for a moment. Everything we can see, every star and galaxy and nebula, every planet and asteroid and grain of cosmic dust, all the matter and energy that we consider to be the universe, represents less than 5% of what actually exists. We are like inhabitants of a vast city who can only see the tiny fraction of buildings that happen to have lights on at night, completely unaware of the enormous dark architecture that surrounds and supports the little we can observe. This invisible cosmos operates according to rules we're only beginning to understand. Dark matter can pass through ordinary matter as if it weren't there, yet its gravitational influence shapes the largest structures in the universe. Dark energy affects the expansion of space itself, determining the ultimate fate of every galaxy, every star, every world. Recent observations suggest that dark energy might not be constant over cosmic time. If confirmed, this would mean that the fundamental properties of space itself are evolving, that the rules governing cosmic expansion have changed throughout the universe's history and might continue changing in ways we cannot predict. The implications are staggering. We inhabit a cosmos where 95% of reality consists of phenomena that remain almost completely mysterious to us. Our models of cosmic evolution, our understanding of structure formation, our predictions about the ultimate fate of the universe, all rest on our limited knowledge of these invisible components. This creates a peculiar situation for conscious beings trying to comprehend cosmic scale. We're not just small relative to the universe, we're blind to most of it. We're like creatures who have evolved to see only a tiny sliver of the electromagnetic spectrum, trying to understand a reality that extends far beyond our sensory capabilities. And yet, through the remarkable tools of mathematics and physics, we can detect the presence of these invisible phenomena. We can map the distribution of dark matter by observing how its gravity bends light from distant galaxies. We can measure the effects of dark energy by studying the brightness of distant supernovae. We can study the invisible cosmos through its influence on the visible one. This suggests something profound about the relationship between consciousness and cosmic reality. Perhaps comprehension doesn't require direct sensory access. Perhaps understanding emerges from the patterns we can detect, the relationships we can measure, the mathematical structures we can construct to describe phenomena beyond our direct experience. In this view, the incomprehensibility of cosmic scale isn't a barrier to understanding. It's an invitation to transcend the limitations of our evolved perspective. Every time we discover something about dark matter or dark energy, every time we map another piece of the invisible cosmos, we expand not just our knowledge, but our capacity for comprehension itself. We are consciousness learning to see beyond its original sensory boundaries. Minds evolved for one scale of reality, stretching to encompass scales that dwarf our imagination. The universe may be incomprehensibly vast and largely invisible, but our response to this incomprehensibility might be our greatest achievement as conscious beings. As we continue this gentle journey into the heart of cosmic mystery, we'll explore what these discoveries mean for our understanding of consciousness itself, and how the very act of contemplating the incomprehensible might change us in ways we're only beginning to understand. As we drift through these contemplations of cosmic immensity, something rather beautiful begins to emerge from the mathematics of scale itself. The universe, it seems, has a peculiar fondness for repeating its own patterns across vastly different orders of magnitude. Consider the delicate spiral arms of our Milky Way galaxy, those graceful curves of stars and gas that sweep outward from the central bulge like cosmic calligraphy written across hundreds of thousands of light years. Now imagine zooming out beyond our galaxy, beyond our local group, beyond even our supercluster, until you can observe the cosmic web itself. What do you see? Those same spiral patterns, those same flowing curves, but now written across structures billions of light years in extent. This phenomenon, which mathematicians call self-similarity, suggests something profound about the fundamental nature of cosmic architecture. The same physical processes that shape matter and energy at one scale seem to operate with remarkable consistency across scales that differ by factors of trillions. Think about a river delta viewed from above, its branching channels spreading like the veins of a leaf. Now consider the neural networks in your brain. They're branching dendrites reaching out to form connections with other neurons. The similarity isn't coincidental. Both systems are shaped by optimization principles that create similar patterns regardless of scale. In the cosmic realm, we see this self-similarity in the way dark matter forms vast filamentary networks that mirror the neural networks of the brain. The cosmic web, with its dense nodes connected by flowing streams of matter, bears an uncanny resemblance to the architecture of consciousness itself. Some researchers have calculated that the number of neurons in a human brain is roughly equivalent to the number of galaxies in the observable universe, while the number of neural connections mirrors the number of stars. This creates a rather poetic possibility. Perhaps consciousness and cosmos are not just connected by the fact that we are made of stellar material, but by deeper structural similarities that operate across scales we can barely fathom. Perhaps the very patterns that give rise to thought and awareness echo the patterns that organize matter and energy on the largest scales imaginable. But here's where this becomes even more intriguing. Recent advances in complexity theory suggest that self-similar patterns often emerge in systems that exist at the edge of chaos, in that delicate balance between order and randomness, where the most interesting behaviors arise. The universe itself might exist in this critical state, neither completely ordered nor completely random, but balanced at the precise point where complexity and consciousness become possible. This raises a fascinating question about the nature of cosmic incomprehensibility. Perhaps the reason we struggle to grasp cosmic scale isn't just because of the vast distances and enormous numbers involved. Perhaps it's because the universe operates according to principles of self-organization and emergent complexity that exist at the very limits of what any conscious system can comprehend about itself. Now, as we continue this meditative journey through scales that dwarf human intuition, we encounter one of the most puzzling aspects of cosmic reality. The universe appears to be fine-tuned for the existence of complexity, structure, and ultimately consciousness itself. Consider the fundamental constants that govern physical reality: the strength of gravity, the mass of the electron, the rate of cosmic expansion, the efficiency of nuclear fusion in stellar cores. Each of these values appears to fall within an extraordinarily narrow range that allows for the formation of atoms, stars, galaxies, and the complex chemistry necessary for life. If gravity were just slightly stronger, stars would burn out too quickly for complex evolution to occur. If it were slightly weaker, matter would never clump together to form stars in the first place. If the strong nuclear force were marginally different, the nuclear reactions that forge heavy elements in stellar cores would be impossible. If the cosmological constant that drives cosmic expansion were even minutely larger, space would expand so rapidly that galaxies could never form. The precision required is breathtaking. Some of these constants must fall within ranges as narrow as 1 part in 1060 for a universe capable of supporting complexity. That's like hitting a target the size of a single atom while blindfolded and standing on the far side of the observable universe. This cosmic fine-tuning creates what physicists call the anthropic puzzle. Why does the universe appear to be so precisely calibrated for the emergence of observers capable of contemplating its fine-tuning? It's as if the cosmos knew we were coming and adjusted its fundamental properties accordingly. One possible answer is the multiverse hypothesis. Perhaps our universe is just one of an infinite number of universes, each with randomly assigned fundamental constants. In such a scenario, we naturally find ourselves in a universe compatible with our existence because we couldn't exist in any other kind. It's a cosmic version of survivor bias taken to its ultimate extreme. But the multiverse hypothesis, while mathematically elegant, pushes the boundaries of incomprehensibility to their absolute limits. If our own universe is mind-bendingly vast and largely unobservable, what does it mean to contemplate an infinite ensemble of such universes, each potentially different in its fundamental laws of physics? Some versions of multiverse theory suggest that every quantum measurement creates new branches of reality, with all possible outcomes occurring in parallel universes. Others propose that cosmic inflation creates an endless series of pocket universes, each with its own randomly assigned physical constants. Still others emerge from string theory suggestion that there might be 500 different ways to configure the fundamental forces of nature. Each of these possibilities expands the scale of reality far beyond anything we've discussed so far. If the multiverse exists, then our observable universe, with its 93 billion light-year diameter and its 2 trillion galaxies, represents an infinitesimally small fraction of a much larger reality that encompasses every possible variation of physical law and cosmic evolution. This creates a peculiar situation for consciousness, attempting to comprehend its place in the cosmic scheme. We might be not just small relative to our universe, but infinitesimal relative to the totality of possible universes. Yet paradoxically, we might also be inevitable, guaranteed to exist somewhere in the infinite expanse of possible realities. As we settle deeper into these contemplations of scale and meaning, let's consider one of the most remarkable discoveries of modern physics. The universe appears to be fundamentally informational in nature, suggesting that reality itself might be best understood not as a collection of particles and forces, but as a vast computational process. This insight emerges from several different areas of physics. In quantum mechanics, the state of any system is described by information, specifically the quantum information encoded in its wave function. When we measure a quantum system, we're not just observing pre-existing properties, we're extracting information that determines the system's future evolution. In cosmology, the holographic principle suggests that all the information contained within any volume of space can be encoded on its boundary. This means that our three-dimensional reality might emerge from information processing occurring on a two-dimensional surface, like a cosmic hologram of unimaginable sophistication. Black hole physics reveals that these extreme objects are not just gravitational monsters that devour matter and energy, but cosmic information processors that encode data about everything they consume on their event horizons. The amount of information a black hole can store is proportional to the area of its surface, not its volume, suggesting that information, not matter or energy, might be the most fundamental aspect of physical reality. When we apply this informational perspective to cosmic scale, something remarkable becomes apparent. The observable universe, with its 1080 atoms and 10^120 bits of information, represents a computational system of extraordinary scope. Every quantum interaction, every particle collision, every stellar fusion reaction contributes to an ongoing cosmic computation that has been running for 13.8 billion years. This computational cosmos processes information at scales that make our most powerful supercomputers look like pocket calculators. The Milky Way galaxy alone contains enough information to require more storage capacity than has ever existed in all of human technology combined. A single supernova explosion processes more information in a few seconds than our entire civilization has generated throughout its history. But perhaps the most remarkable aspect of this cosmic computation is that it has given rise to subsystems capable of understanding the computation itself. Consciousness represents the universe developing the ability to process information about its own information processing. We are cosmic algorithms that have evolved the capacity to contemplate the algorithmic nature of reality. This creates a beautiful, recursive loop. The universe computes itself into existence, develops computational subsystems like brains, capable of modeling cosmic processes, and through these subsystems begins to understand its own computational nature. We are the universe's way of debugging its own code. As we continue our gentle exploration of cosmic vastness, we must consider not just the spatial scales that stretch our understanding, but the temporal scales that make human history seem like the briefest flicker in an eternal night. The universe is 13.8 billion years old. To put this in perspective, if the entire history of the cosmos were compressed into a single year, human civilization would occupy only the last few seconds, before midnight on December 31st. All of recorded history, every empire that ever rose and fell, every work of art ever created, every scientific discovery ever made, would fit into the final fraction of the final second of the cosmic year. But even this analogy fails to capture the true scope of cosmic time. The universe has already lived through what cosmologists call its stelliferous era, the age of star formation and stellar evolution. We exist during the relatively brief period when stars are actively forming, fusing hydrogen into heavier elements, and creating the complex chemistry necessary for life. Looking toward the future, the temporal scales become even more mind-bending. In about 5 billion years, our Sun will exhaust its hydrogen fuel and begin its death as a red giant star. In 4.5 billion years, the Andromeda Galaxy will collide with the Milky Way, fundamentally reshaping our local cosmic environment. These events seem impossibly distant from our human perspective, but they represent the near future in cosmic terms. On longer timescales, the expansion and cooling of the universe will eventually make star formation impossible. In about 100 trillion years, the last stars will burn out, leaving behind a cosmos populated only by white dwarfs, neutron stars, and black holes. Even these remnants have finite lifetimes. Protons themselves may decay after 10^34 years, causing all atomic matter to slowly dissolve into radiation and elementary particles. Eventually, even black holes will evaporate through Hawking radiation, returning their mass energy to the vacuum of space. The largest black holes will take 100 years to completely evaporate, a timescale so vast that the current age of the universe seems like an instant in comparison. After black hole evaporation, the universe will enter what cosmologists call the heat death phase, an era of maximum entropy where no further organized structures can form. The cosmos will consist of a thin soup of elementary particles and photons, growing ever more dilute as space continues to expand. These temporal scales reveal something profound about our place in cosmic history. We exist during what might be called the universe's childhood, in the brief era when stars shine and complex structures can form and evolve. We are witnesses to cosmic dawn, observers of the universe's most creative and dynamic phase. Yet even our temporal insignificance carries a kind of beauty. Every moment of consciousness, every instant of wonder or love or curiosity occurs against the backdrop of these incomprehensible time scales. The very brevity of our existence might be what gives it meaning, like a delicate flower blooming in an infinite winter. As we approach the deeper waters of our exploration, let's pause to consider what these incomprehensible scales mean for conscious beings like ourselves, evolved to navigate environments measured in human steps and human lifetimes. There's a particular kind of vertigo that comes from truly contemplating cosmic scale. It's not the physical dizziness of looking down from a great height, but a kind of existential vertigo that arises when we realize how vanishingly small we are in the grand scheme of things. Psychologists call this the overview effect, though it usually refers to the perspective shift that astronauts experience when viewing Earth from space. But there's a deeper version of this effect that comes from contemplating not just our planet in its cosmic context, but consciousness itself in the context of cosmic evolution. We are arrangements of atoms that took 13.8 billion years to evolve the capacity to contemplate the 13.8 billion year process that created them. We are the universe's way of knowing itself, but we are also incredibly fragile and temporary manifestations of that cosmic self-awareness. This realization can be deeply humbling, but it can also be profoundly liberating. If we are truly as insignificant as cosmic scale suggests, then perhaps our failures and anxieties and daily struggles matter less than we imagine. The mortgage payment that keeps you awake at night, the career decision that feels so momentous, the social embarrassment that replays in your mind, all of these concerns exist on scales so small compared to cosmic reality that they barely register. Yet paradoxically, this same insignificance might be what makes consciousness precious. In a universe of such vast scale and apparent indifference, the fact that matter has organized itself into patterns capable of wonder, love, creativity, and understanding seems miraculous. Every act of kindness, every moment of beauty, every insight into the nature of reality represents something unprecedented emerging from cosmic processes that operate on scales far beyond human comprehension. There's a particular kind of peace that comes from accepting our cosmic insignificance, while simultaneously embracing the miracle of our existence. It's the peace of recognizing that we don't need to be cosmically important to be meaningful. Our meaning emerges not from our size or longevity, but from our capacity to experience, to understand, to create, and to care. This perspective shifts our relationship with uncertainty and mystery. Instead of seeing the incomprehensibility of cosmic scale as a limitation of human understanding, we might see it as an invitation to humility and wonder. We are consciousness exploring a reality that extends far beyond the boundaries of any possible comprehension, and that exploration itself might be among the most remarkable phenomena in the universe. Now, as we drift deeper into this meditation on scale and comprehension, something rather beautiful begins to emerge from the very act of contemplating the incomprehensible. Each attempt to understand cosmic scale changes our capacity for understanding itself. When you first learned that the nearest star is 4.3 light-years away, that distance was probably incomprehensible. But through repeated exposure to astronomical scales, through analogies and comparisons and mathematical relationships, your mind has gradually expanded its capacity to work with such distances. You still can't truly comprehend 4.3 light-years, but you can think about it, reason with it, use it as a stepping stone to even larger concepts. This suggests something profound about the nature of consciousness comprehension, perhaps the very act of reaching and cosmic reality. Understanding might not require complete toward incomprehensible scales, expands our cognitive capacity in ways that make us more fully conscious, more deeply aware of the nature of existence itself. Think about how your perspective has shifted during our journey tonight. We began with familiar scales, the room you're in, the distance you can see. Gradually, we expanded outward through stellar distances, galactic scales, cosmic structures that span billions of light-years. Each step required a conceptual leap, a stretching of imagination that expanded your capacity for the next conceptual leap. And so, here we are at the end of our gentle journey, through scales that dwarf human imagination, having travelled from the familiar confines of our earthbound perspective to the very edges of cosmic comprehension. We've discovered that the universe is not just incomprehensibly vast, but beautifully, mysteriously, and perhaps necessarily so. The grain of sand that covers thousands of galaxies when held against the night sky, the cosmic web that mirrors the neural networks in your brain, the quantum uncertainty that underlies all measurement, the dark architecture that comprises 95% of reality, all of these point to something profound about the nature of existence itself. We are not separate observers of cosmic scale, we are expressions of it, consciousness emerging from the very processes we struggle to comprehend. Perhaps the most beautiful aspect of cosmic incomprehensibility is that it invites us into a deeper relationship with mystery itself. In a universe where our observable bubble contains 2 trillion galaxies, where space itself expands faster than light can travel, where consciousness arises from quantum processes we barely understand, wonder becomes not just an emotional response but a fundamental way of being. Tonight, as you drift towards sleep, you carry with you the quiet knowledge that you are made of stellar material, contemplating stellar processes, quantum phenomena, pondering quantum reality, the universe becoming aware of itself through the miracle of your consciousness. The incomprehensible vastness that surrounds us doesn't diminish our significance, it illuminates the extraordinary improbability and precious beauty of awareness itself. Sleep well, fellow traveler in this cosmic mystery. And if you're curious about how your consciousness might be connected to the quantum foundations of reality itself, you might find our next exploration fascinating. Quantum consciousness theory, how your brain connects to the universe. Until then, may your dreams be filled with the gentle enormity of it all.